Hello, today we are going to be looking at our second probability review. So the first section is talking about the likelihood of an event, so we are going to determine whether each event is impossible, unlikely, equally likely, likely, or certain. So if you guys remember at the very beginning of this unit, we talked about the probability number line that ranges from 0 to 1. And when you have a probability of 0, that means that you have a impossible probability. When you have a probability of 1, that means that you are certain of an event occurring. In between 0 and 1, you have 1/2, which indicates that your probability would be equally likely. And then in between 0 and 1/2, it just depends on whatever your fraction is. We indicate this region as unlikely. And then the region from 1/2 to 1 as likely. Okay, so whenever you guys are asked what the likelihood of an event is, you first have to find the probability and then indicate where it falls at on our number line. So the first one says rolling an odd number on a number cube. Well, thinking of the numbers on the number cube, we have numbers 1 through 6. And of the numbers 1 through 6, we have 3 numbers that are odd. That's 1, 3, and 5. So if we have 3 numbers that are odd, we have a probability of 3 out of 6 total, which reduces to 1/2. So the likelihood of an odd number showing up, 1/2, we say that it would be equally likely. Okay, looking at the second one, so rolling a 2 or a 3 on a number cube. So there's only 1 2 and 1 3 on a number cube. So the probability of rolling a 2 or a 3 is 2 out of 6 total, because there's only 2 2s or 3s out of 6 numbers total on a number cube. And 2 out of 6 reduces to 1/3. And as we know, 1/3 is within this region between 0 and 1/2, so we would say that it is unlikely. Number 3, rolling a number greater than 1 on a number cube. So all numbers greater than 1 on a number cube are 2, 3, 4, 5, and 6. So there's 5 out of 6 numbers on the number cube that are greater than 1. So 5 out of 6 would fall in between the 1/2 and 1 category, so we would say that it is likely that that would happen. And then the last one, rolling a number 1 through 6 on a number cube. Well, those are all the numbers on a number cube, so we know for sure that when we roll a number cube, we are going to get a number 1 through 6. So we know for sure that this would be certain that this would occur. Okay, moving on to complementary events. So if 2 events are complementary, when added together, they must always equal 1. So in other words, it has to equal 100%. Okay, so if probability of event A is 0.39, to get your probability of event B, you're just going to take 1 minus the 0.39. So 1 minus 0.39 gives you 0.61. Same thing when you have a fraction. So if you're trying to find the probability of event B when probability of event A is 5/6, you're just going to take 1 minus 5/6, and you can do this in your calculator. Or if 5 out of 6 was your probability, that means that you only have 1/6 of it left. And then probability of event A for the last one is 24%. So you're not going to take 1 minus 24. You want to take 100% minus that 24% to figure out the complement event, and that will give us 76%. Okay, so now moving on to some basic probability examples. So find the probability of each event, write each as a fraction, decimal, and a percent. So the probability of getting a 3 or a 5, so there's only 2, 3, or 5s on a number cube out of 6 numbers total. So the fraction probability of getting a 3 or a 5 is 2 out of 6, which reduces to 1/3. And remember, to change a fraction to a decimal, all that you guys are going to do is divide. So 1 divided by 3 is 0.3 repeating. And then to change a decimal into a percent, you just move your decimal point 2 times to the right. So if we have 0.3 repeating, and I move my decimal point 2 times to the right, 0.3 repeating would be 33.3 repeating percent. Okay, next one, probability of getting a composite number. So a composite number means that you have more than one factor that goes into a number. So only 1 times 1 gives you 1, so that's not composite. The number 2 on a number cube, only 1 times 2 gives you 2, so that's not composite. 3, only 1 times 3 gives you 3, so that's not composite. 4, though, is composite because 1 times 4 is 4 and 2 times 2 is 4, so it has multiple factors. So 4 is 1. 5 is not because only 1 times 5 is 5. And 6 is composite because 1 times 6 is 6 and also 2 times 3. So only 4 and 6 were composite numbers. So once again, that just means we have a 2/6 probability of getting a composite number. So our fraction, our decimal, and our percent is going to be the same. All right, probability of getting a factor of 6. So these are the numbers that we can multiply together to get 6. So if we're thinking on a number cube, we have 1 times 6, which gives us 6. So 1 and 6 would be factors, and also 2 and 3, because 2 times 3 is also 6. So that means that we have 4 numbers total out of 6. That would be a factor of 6, and 4/6 reduces to 2/3. So let's change this into a decimal. So just take 2 divided by 3, and that gives us 0.6 repeating. And again, if we were to change this into a percent, just move that decimal point 2 times to the right, and we would get 66.6 repeating percent. All right, next part is using the spinner over here. So probability of getting green. So we need to count all the greens, and I see 2 out of, and then just count the total. So 1, 2, 3, 4, 5, 6. So we have a 2/6 chance of getting green. And as we said up here, 2/6 is equivalent to 1/3, which is the same thing as 0.3 repeating, which is the same thing as 33.3 repeating percent. Probability getting purple or blue, so count all the purples and blues. We have 1, 2, 3 out of 6 total. So 3/6 is equivalent to 1/2. So 1/2 as a decimal, if you were to take 1 divided by 2, is 0.5. And then move that decimal point 2 times to the right to get its percentage, which would be 50%. And then the last one here, probability getting not red. So you want to count everything else other than red. So we have 1, 2, 3, 4, 5. So we have 5 of them out of 6 that are not red. So changing this into its decimal form, 5 divided by 6 is 0.83 repeating. And then changing it into its percentage form, just move that decimal point 2 times to the right, and we would get 83.3%. And that 3 would be repeating. Okay, moving on to our second page here, we're talking about tree diagrams. So we're going to make a tree diagram for flipping a coin 3 times and then giving it sample space. So remember, when you are creating a tree diagram, you want to create it based off of the outcomes of the events that are happening. So for example, for flipping a coin, the outcomes are heads or tails. So I should only see H's and T's within my tree diagram and nothing about the coins itself, okay? So when I flip the first coin, the outcomes that I can get are heads or tails. So I'm going to start my tree with H and T. Then when I go to flip my second coin, because I'm going to flip it 3 times, again, my outcomes are heads or tails. So I'm going to have 2 branches going off of my outcomes before it. And then I'm flipping the coin 1 more time, so once again my outcomes are going to be heads and tails, so I'm going to have 2 branches going off of each of these, and I'm just going to label them with heads, tails, heads, tails, heads, tails, and heads, tails. So again, your first event was flipping the coin the first time, and you can get heads or tails. Then you flip it the second time, you can get heads or tails, and then same thing with the third time, okay? So when I go to list the sample space, I'm just listing all the outcomes that could happen. So if I were to count my last column here, I have 8 different outcomes, so there's 8 outcomes possible. So in my sample space, I need to list all 8 of them. So my first one here would be heads, heads, heads. My second one would be heads, heads, tail. Then my next one would be heads, tail, head. And then heads, tail, tail. So that took care of the first part, and to do it you're just looking at your last one and following the branch all the way back to be able to figure out all 4 of those outcomes, okay? And then you're just going to do the same thing down here with the tail. So my first outcome would be tails, head, head. Next one would be tail, head, tail. Then tail, tail, head. And then tail, tail, tail. Okay, so this question is asking what would be the probability that the coin lands on 3 heads. So looking at our sample space, how many 3 heads did we have? We only had 1 out of 8 outcomes total. So the probability of getting 3 heads would be a 1/8 chance. Okay, next one, number 14, you are going to a restaurant for lunch and you are to choose a soup, salad, and a sandwich from the menu. You can choose from tortellini or lentil for your soup, Caesar or macaroni for your salad, and roast beef, ham, or turkey for your sandwich. So they want us to create a tree diagram and then create a sample space. So when you're creating your tree diagram, you always want to start with the thing that you are choosing first. So in this case, they want us to choose the soup first. So we can pick tortellini, or we can pick the lentil. Okay, then go on to the next thing that you're choosing, which in this case is a salad. So you can choose Caesar or macaroni. So we're going to have 2 branches going off of our soups for Caesar salad or macaroni salad. And then the last thing that we're choosing is our sandwich, and we can choose roast beef, ham, or turkey. So I need 3 branches going off of each of my salad. And I'm going to label them roast beef, ham, and turkey. Okay, so this is what our tree should look like when we're done. So again, if I were to add up my last column here, I would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 outcomes. So when I go to list my sample space, again, I am just listing all the 12 outcomes possible. So looking at my first outcome here, I had roast beef, Caesar, tortellini, and then you just always want to put it in the order that you have your tree going left to right. So first option is tortellini. I'm just going to label it with TOR. Then we have Caesar and then roast beef. Or I can get tortellini with Caesar with ham, or tortellini with Caesar with turkey. Then moving down here, option up 4, I can get tortellini with mac and cheese with roast beef. Or I can get tortellini with Caesar with ham, or I can get tortellini with Caesar with turkey. So that took care of my tortellini for the soup. So now I'm going to move down here to the lentil, and again I'm just going to look at my options and work backwards and then write it as if they were looking at my tree. So then I could have lentil with Caesar roast beef, lentil Caesar ham, or lentil Caesar turkey. And then to finish up the tree down here, I can get lentil with mac and roast beef, lentil with mac and ham, or lentil with mac and turkey. So again, when you guys get done, if you guys set up here that you had 12 outcomes, you should have all 12 outcomes in your sample space listed. Okay. Moving on to the counting principle now. So remember, the counting principle is just telling you how many outcomes that there are by just multiplying all of your events together. So number 15 says, confirm your answer from the tree diagram on question number 13 by using the counting principle. So question 13, we were flipping a coin, and remember, we had 2 outcomes per event that was happening. So counting principle says you're just going to multiply those events together. So flipping the coin the first time, I had 2 outcomes. Flipping the coin the second time, I had 2 outcomes. And then flipping the coin the third time, I still had 2 outcomes. So if I were to multiply those together, I should have had 8 different outcomes. And if you guys look, we did have 8 different outcomes. Number 16, confirm your answer from the tree diagram on question number 14 by using the counting principle. So again, you're just multiplying the events of how many possibilities that you had. So we had 2 soups, 2 salads, and 3 sandwiches. So I was going to multiply 2 times 2 times 3, and that would give me 12, which is what we got back here. Next one, you have 8 different keys and 6 different marbles. How many outcomes are possible? So again, you're just going to multiply your 2 events together. So 8 times 6 would give us 48 different outcomes. And then you have to be careful with number 18 whenever it's talking about digits and letters, because a lot of students, they just want to multiply 3 times 3. But that is not correct, because when you're talking about digits, think of like the numbers on your computer, okay, or on your telephone, on your cell phone. You have more than 3 digits, right? You have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So really, when you're talking about digits, you have 10 numbers to choose from. So when you're trying to create a password that has 3 digits and 3 letters, you should really be multiplying 6 different outcomes here. So digits, if we have 3 digits, again, digits are the numbers 0 through 9, so you have 10 total that you're choosing from, and you're doing that for each one of the digits that you're choosing. So you should have 10 times 10 times 10, so again, these are talking about the digits. And then for your letters, so think about how many letters we can choose from in our alphabet. We have 26 different letters, so for my last 3 numbers, I have 26 different letters I can choose for my first letter, 26 for my second letter I choose, and then 26 for my third. So all that I'm doing is I'm going to multiply all those numbers together, and I get 1757600. So I get 17,576,000. All right, next section here is talking about predictions. So remember, whenever you are talking about predictions, you will be setting up proportions. So Adam made 13 out of 20 free throw shots in practice today. Predict how many he would make in practice tomorrow if he were to shoot 50 free throw shots based off of his experimental probability. So his experimental probability is what you're going to start with here. So the first day he made 13 out of 20 shots, and then we are trying to figure out if he were to keep up his experimental probability and he were to attempt 50 tomorrow at practice, how many would we expect him to make? Okay, so again, you start with the theoretical or experimental probability, and then you put it x over however many times you're trying to figure out, and then you just solve it. So 20 times x is 20x, 13 times 50 is 650, divide both sides by 20. So 650 divided by 20 is 32.5. So when we're predicting, we always want to round it to the nearest whole number. So we'll round this to approximately 33 free throw shots. Okay, moving on to number 20. So if you roll a number cube 20 times, about how many times you expect to roll a number greater than 4. So this time we need to find the theoretical probability of rolling a number greater than 4. So thinking of the numbers on the number cube, numbers greater than 4 are only 5 and 6. So you only have 2 out of 6 numbers that are greater than 4 on a number cube. And then we're trying to figure out how many times out of 20 would we also expect to get a number greater than 4. Okay, so here's our proportion. So now we can just cross multiply. So that would be 6x equals 40. Divide both sides by 6. So 40 divided by 6 is 6.6 repeating. So again, we'll just round it. So we'll say approximately 7 times. All right, and 30 spins, so we're going to use the spinner. How often can you expect to get a number that is a multiple of 2? So multiples of 2 is when you're taking 2 times 1, 2 times 2, 2 times 3, and so on. So multiples of 2's in this case on the spinner would be 2, 4, and 6. So there's 3 numbers that are a multiple of 2 out of 6 numbers total. And we're trying to figure out if we were to spin it 30 times, how many would we predict to get that? So again, just cross multiply. 6 times x is 6x. 3 times 3 is 90. Divide both sides by 6. So 90 divided by 6 gives us 15. All right, and then this last one here. So in 200 spins, about how often can you expect to get a number greater than 2? So numbers greater than 2 on our spinner here are 3, 4, 5, and 6. So there's 4 numbers greater than 2 out of 6 numbers total. And we're trying to figure out how many out of 200 spins would we also predict to get a number greater than 2. Okay, so 6 times x is 6x. 4 times 200 is 800. Divide both sides by 6. So 800 divided by 6 here would give us 133.3 repeating. So again, we'll just round it to the nearest whole number. So we'll say approximately 133 times. All right, and moving on to the back page. So we have a number cube that's rolled 50 times, and the results are shown in the graph below. So what is the experimental probability of rolling of 2? So the experimental probability is coming from the table, since this was done multiple times. So probability of rolling a 2, notice how they got the number 2 8 out of 50 times. So the experimental probability of rolling a 2 would be 8 out of 50. And when you reduce that by reducing it by 2, you would get 4 out of 25. Then, whenever it's asking what's the theoretical probability of rolling a 2, this is what's supposed to happen if you do it one time. So how many number 2's on a die? 1 out of 6 total. So the theoretical probability of rolling a 2 would be 1/6. Next portion here says to compare the experimental probability of rolling a 2 to its theoretical. So what I'm trying to do here is I need to compare these two by figuring out which one's greater, which one's not, which one's more likely to happen. So again, I think it's easier to divide these, to change them into decimals whenever you're trying to compare. So 4 out of 25 is 0.16, and then 1 divided by 6 is 0.16 repeating. So since this one is repeating and this one's not, the theoretical probability is greater than the experimental probability. So down here, you would say the theoretical probability is more likely to happen compared to its experimental because its probability is greater. Okay, so that's a good sentence for you guys to write on your test. And then just a couple more examples here. So what's the experimental probability of not rolling a 6? So we're going to go back up here to our table because that was talking about the experiment that happened. And we just need to add all of the outcomes for 1, 2, 3, 4, and 5 and not include 6. So if I were to add 10 plus 8 plus 6 plus 9 plus 5, that will give me 38. So the probability of not rolling a 6 would be 38 out of 50 times total. And again, if I were to reduce that by 2, 38 divided by 2 is 19, and 50 divided by 2 is 25. And that is reduced all the way. And then theoretically, what's supposed to happen when you not roll a 6? So you have a 1, 2, 3, 4, and 5. So you have 5 numbers total out of 6 numbers total on the die. That would not give you a 6. And that is it. So if you guys have any questions, just let your teacher know.